Hello and welcome to this video where I will be explaining how to implement genetic algorithms for the following task that was set for a natural computing lab on the 1st of December 2016. So let's start off with explaining the scenario itself. So we have a chromosome structure that has 8 genes, and each of these genes could be between 0 and 9. To calculate the fitness of this gene, or of this chromosome, we'd simply add up each of the 2 pairs of chromosomes, so 0 and 1, 2 and 3, 4 and 5, 6 and 7, and then we minus the first pair with the second pair, then add the 4th and 5th pair, the 3rd pair, and then minus the last pair. So this will produce a number, and as this is a maximization problem, we'll be trying to find the chromosomes with the highest fitness. Those would be the better chromosomes. So I'll be wanting to be finding the fitness of these chromosomes. So we have these chromosomes that are in this format that was on the previous slide, and we need to find their fitness. We'll be using the formula, the fitness function from before. So let's put it into the format. And the first chromosome will equal 9, then 23, then minus 16, then minus 19. Now that we have all the fitnesses calculated, why don't we just put them into a table? We want to sort our chromosomes by their fitness, and as this is a maximization problem, we'll be wanting the largest positive fitness at the top. In other words, we'll want 23 on the top, then followed by 9, followed by chromosome 1, which has a fitness of 9, then chromosome 3 with a fitness of minus 16, and chromosome 4 with a fitness of minus 19. And this is currently our order. So genetic algorithms require crossover to be able to converge onto an optimum solution. So why don't we do that with our current chromosomes? We'll be using these types of crossover in the implementation, so single point, 2-point crossover, uniform crossover. But this slide is here just for a quick reminder for those people who don't remember how the different types of crossover work. So we've got a diagram here showing that single point crossover just takes at a single point and then they just swap one side with the other. 2-point takes 2 points and it swaps the middle part. And uniform crossover just takes random points and swaps those. For more information, visit the link that is displayed on the screen. And for more information about crossover and genetic algorithms, the link will be in the description. So why don't we just start with single point crossover. This will be applied to the best 2 chromosomes. So the 2 best chromosomes we had were chromosome 2 with a fitness of 23 and chromosome 1 with a fitness of 9. We'll be taking the single point right down the center, so that's after the third gene number 3 if we're counting from 0. And then we would simply replace everything after that line and flip that. So to replace, we'd simply swap one side with the other, and as we can see in the child chromosomes, I've swapped the last 4 genes of each chromosome to create the 2 new child ones. Why don't we move on to 2-point crossover now? For this we'll be using the 2nd and 3rd best chromosomes, which was chromosome 1 with a fitness of 9 and chromosome 3 with a fitness of minus 16. We've taken these 2 points, so I've put a point after gene 1 if we're counting from 0, and I've put the other one after gene 5. And for this, we simply swap the genes between the 2 points. This again creates 2 more chromosomes, displayed as child 3 and child 4. And for the final type of crossover, which is uniform crossover, we'll be using the first and third best chromosomes. Chromosome 2 with a fitness of 23, and chromosome 3 with a fitness of -16. Uniform crossover takes random points and swaps genes at those points, so if we swap these points, we'll get these 2 child chromosomes. So now that we have our child chromosomes, let's calculate the fitness of each. So we have all our child chromosomes that I just made in the crossover, and we'll be using the fitness function to find the fitnesses for each of the chromosomes, and that will look like this. But has there been any improvement from our original chromosomes? Why don't we find out? So here's all the child chromosomes and the parent chromosomes. Why don't we sort this with the highest fitness at the top? Well, as it shows, none of the child chromosomes managed to have a higher fitness than the parent chromosome CH2. But all the child chromosomes were fitter than half of the parents, meaning that there is some improvement from the average, but not objectively because they were not higher than chromosome 2. So you may be thinking or wondering, what is the optimum solution that we're trying to go for? I suggest that it's 99009900. If we were to test this using the fitness function, we have this formula, which then turns to this. Get rid of the zeros, and we've got 36. I propose that 36 is the highest fitness that we can go for, and the only solution with this fitness is 99009900. For as we cannot add 1 to either of the 9s, because 9 is the highest that we can get in our range for each gene, and if we add 1 to any of the zeros, the fitness would be lower than 36, which would then have a worse fitness. Therefore, 36 is the highest fitness, and 99009900 is the optimum solution. But with genetic algorithms, we tend to see crossover and mutation as well, but we haven't seen mutation yet. So could we say that it is necessary? We've seen that crossover improved the average of the fitnesses, so do we really need mutation? Well, let's have a look at what crossover and mutation do in genetic algorithms. Crossover attempts to exploit the current situation and tries to converge onto the best answer. Mutation is more about exploration and attempts to find new arrangements, but doesn't converge. However, if we were to stick with crossover, it means that the program will more likely be stuck to a local minima and would not improve. Therefore, it would not find a better fitness. With mutation, you may end up getting the best solution at some point, but it is down to pure chance and the program could end up running indefinitely. So, mutation and crossover are both needed as crossover converges onto the optimum solution whilst mutation tries to explore the search space. Now, I have implemented my own version of this, and I will be sharing this as well in the link in the description below, and links are on screen as well. If you'd like to download my code, I have 3 different versions with the zip file that comes in it. The first part is for part 1 of this video. The second part is for part 2 in the video, and the final part is my full implementation, which includes crossover and mutation. Please download it and play about with the code to find the best parameters. If you're also interested, I have written some blog notes about this on my website. Links for these are on the screen and in the description. Thank you for watching.